Okay, so what we did last time is we had an idea of a vector, which was basically a function watcher. It watched how the function changed. It had a basis dimension n, the same as the manifold. And then in order to describe displacements, and in other words, something that stayed on the manifold as you turned, we introduced the idea of diffeomorphism, which basically mapped the manifold onto itself with an extra parameter that told you how far the points were separated. And then we said it had the properties that if you have two of these parameters, then it just behaved like distance, namely the diffeomorphism of one followed by the diffeomorphism of the second one was simply the thing of you went twice the sum of the two distance along the diffeomorphism for the map. So it's basically a parameterized map. And if t is equal to 0, it's the identity map. And then what we did also is we wanted to try and associate a vector with a particular diffeomorphism. And so what we did was we said, let us look at a fixed point P. In other words, we fix an element of M, and then we look at the impact of changing this other parameter R for your fixed P. And what you then have is a restricted map from R to M, your manifold. And that restricted map meets the definition of a curve. So effectively what we've done by restricting this diffeomorphism phi t to a particular point, we've restricted it to simply be a map from R to M, which is a curve, and this particular curve that we associated with that point is that phi of t, and we called it the orbit. And remember, the moment we have a curve, we could always associate a tangent vector with it, which was exactly the components of the tangent vector that you map to in Rn with your chart. Okay. And so what we can do now is with this particular orbit that passes through P at times t0, we can define the vector at P to be this tangent to the curve at times t equals to 0. So it's a very reasonably complicated construction, but all it's doing is it's connecting the idea of a vector that's associated with your manifold, that's associated with the functions, all functions that map the manifold to R, with the actual idea of motion on the manifold that's encompassed by your diffeomorphism phi. Okay, so basically a vector so defined is thought of an infinitesimal generator of a smooth transformation of M, or the flow direction. So if you think of ODEs, where we had the ordinary differential equations just in Rn, we basically had x dot equals to a whole bunch of functions on the right-hand side. I said view those functions on the right-hand side as a vector that's pointing in phase space. Okay, and this is the same thing that we're doing here. In some sense, we've got this idea of a diffeomorphism, which is through the point, which is simply lines going through the point. Its tangent vector basically tells you the direction of which the line is pointing, but it isn't the line itself. The same relationship exists between these sort of orbits of the diffeomorphism and the vectors on the manifold itself. So that's where the connection takes place. The vectors themselves don't stay in the manifold, they live in a different space, but they are connected with motions on the manifold the moment you say that you can view them as tangent space to the orbits of this diffeomorphism. And so one of the questions you can then go and ask is, if you're given any smooth vector field, and remember the way we defined smooth of a vector field if we're working on a basis was simply that all its components were smooth. Okay. So if you're given any smooth vector field on M, is it possible to find a family of curves on M that have the property that one and only one curve passes through each point on P? It's basically the same as trying to say, given a vector field in Rn, can you get a phase portrait where you actually work out your trajectories in dynamical systems such that they pass through a particular point? And the answer is actually yes, and we use what we know of dynamical systems in Rn, because we can always go to Rn with the charts to actually prove that. So I'm not going to do the proof in gory detail, I'm just going to give you the main steps. But the answer is basically, if you have a given vector field V, it's on M, then the family of curves that basically have the property that one and only one curve passes through each point on M, okay, that has the tangent basically being the smooth vector field. This family of curves we then call the integral curves on V, of V. In other words, what we did in these two blocks is we said we had these diffeomorphisms, we had these curves, we had each curve going through a point giving us an orbit, and then we could easily associate a vector with that orbit, okay? That's simply similar to saying, given a whole batch of curves, you can always get a tangent vector. We're now doing the reverse and saying, if we're given a smooth vector field, will we always be able to get the curves that in some sense match the vector field? And so that it goes one way and the other way, so the identification is basically a one-to-one onto, and that's what we're doing now, okay? And basically this family of curves that always have the vector field tangent to them is very much akin to the phase portraits we work in dynamical systems in Rn. And in fact, we get them exactly from that. So the argument basically goes, yes, it's possible always if you have a smooth vector field to find a family of curves that correspond, that have it as tangent. And the way we prove that is we simply say, let's choose a chart near P, okay, just like we did when we proved that the dimension of the vector space is the same as the dimension of the manifold. And then the problem of finding these integral curves, in other words, given the vector field, the curves that go through it, is the same as solving a whole bunch of ODEs that are like this. For example, remember we connected the tangent vector with the actual of the manifold's components with the tangent vector on the Rn where the chart maps it to actual real physical components. And we simply say this problem of finding the integral curves on the manifold is the same as solving ODEs where your coordinates of the point on the chart is simply equals to the vector field that you've specified. Okay, so, and then what we have basically is that the V component is the youth component of V, the V mu is the youth component of V, and on this coordinate basis, ddx mu, okay, so remember the vector field has this coordinate basis that basically helps it ask the question of how the function is changing, and we have then this uniqueness and existence theorems of ODEs in Rn that basically guarantees that you can always solve this problem and that it is unique, and therefore you're going to always have a unique solution existing here, and so you're actually always going to be able to get this curve in Rn.
Sorry. Goedemorgen, ik is op zoek naar Pieter Lots.
Ik weet niet.
Dat was in mathematics science building.
Yeah, sorry, I'm busy recording. Can you ask Timothy over there?
There's no one here but that.
Right. So the fact that a unique solution exists to this problem basically means we can always get the actual coordinates out given the vector field, and at least in a region close to the point where we're considering. Okay, so what this means is that every smooth vector field V has a unique family of integral curves associated with it. And so what we then can go and do is we can go and define this phi of t of p equals to q to be the point lying at parameter t along this curve. Okay, so the basic takeaway is that there is a one-to-one relationship between your vector field and the curves that it describes. And the way we find, if we're given a vector field, the way we find the curves is we simply can solve these component equations which is the same as solving an ODE. And so we inherit everything we know from the ODEs and Rn onto the manifold, provided we separate their roles in terms of these diffeomorphisms that give you the curve and the vector field that we've defined it formally in the last couple of slides. Okay. So now we have displacements. The next thing we're going to need is basically the idea of a commutator. So if you remember what I did when we started working out the differential, using the Hamiltonian formalism to find your orbits for geodesics, just to get you guys started, there was this thing called the Poisson brackets that we used. So the commutator is not it's not formally the same thing, but the fact that the two eventually can be drawn together comes very much from the fact that you have the idea of a commutator. Okay, so what the commutator does, it basically, in some sense, looks at the difference of the action of two vector fields. So, for example, if you just think of Rn, suppose you have a function and you take the derivative of the function in one direction, and then you take the derivative of the function in another direction, okay, you get an answer. But you could ask the question, what happens if I first took the derivative of the function in the second direction and then took the derivative of the function in the first direction? In other words, switch the order of differentiations. What's the difference? So if you're just working in Cartesian coordinates like x and y, there's no difference, right? But if you took a directional derivative, in other words, some vector times dx times some vector times dy, when you apply the second derivative, you're actually going to differentiate the component, have a part that differentiates the components, and then also has the coordinate basis. Then you are actually going to get a difference. So what this does is basically formulates how those differences, those things work. So if you have any two smooth vector fields, say v and w, okay, you can always define a new vector field, v comma w, in the following way, and it's called the commutator of v and w. Okay, and you can define it to be v comma w, which is simply v applied to w that's already been applied to f, minus w applied to v that's applied to f. Okay, so it simply is changing the order. And so if you want a very basic example, say for example v is x times d dx and w is y times d dx plus d dy. Okay, then if you first apply the first operator, you're going to get something to the next. If you apply that operator to the next one, to a function, you're going to get something. But if you switch the two, you're going to get something different. And so all this commutator does is it keeps track of the difference. Okay, now there is, in the special case where your vector field is just the basis vectors, then they commute. So if suppose you have x of mu and x of eta, they are two vector fields in the coordinate basis. Okay, then what you're going to have is x of mu and x of eta are going to equals to 0. And what that basically says, if you have a function, remember your coordinate basis is just d dx of something. So if you have a function of x and y, and you take d dx of x and y, and you follow it, say, with d dy of that, and you switch it, then it's the same thing, because d dx, d dy is the same as d dy, d dx. Okay, so in that case, this bracket or the commutator is 0. But the moment you actually have components coming in and the vectors aren't basis vectors, then it's very often not 0. Okay. And so the reason basically that this thing is 0 is that mixed partial derivatives on Rn don't depend on the order of differentiation. Okay. However, for general vectors, that's not so. So what it's basically saying, this guy is equals to that guy, where you simply switched which thing you're differentiating with respect to, and therefore your commutator vanishes, because this basically, the difference between the two is exactly what this commutator stands for. Okay, so the inverse is also true, okay? And it's the way sometimes, if I don't know what the coordinates are and I don't know what the chart is, when I start solving or trying to write down the coordinates, say in axisymmetry, then I actually use this as the definition of my coordinate basis without ever writing down coordinates. So the inverse is true. If you have a linearly independent collection of non-vanishing vector fields in the manifold, okay, and they have the property that they commute. In other words, if you switch their order and you apply them to a vector field that's 0, then I can always, a chart for which they coordinate basis vectors can always be found. Okay, so, and this I'm not going to prove, but it is very, very useful if you start from absolute abstract manifold and you actually want to start choosing coordinates that are suited to the manifold. This feature is, you say you start with vectors, you don't even write down a chart, and you simply use this feature that they commute to say that's the coordinate basis, and you start working out consequences from there. That's pretty advanced, but I am actually using this, and a student of myself that worked at Caltech basically used this feature a lot when we try to solve the axisymmetric Einstein equations. So it's a very rigorous way of working with the commutator. Okay, so that's just a definition of the commutator. You simply have one vector field, you express it on the coordinate basis, you apply it, you apply another one, and you change the order. And you keep in mind that because the partial derivatives commute, the order doesn't matter there, the basis vectors themselves commute, so you can use your commutator for that. Okay, so that's the most final machinery, or the piece of machinery with vectors. What I now want to go and look at is basically define what a tensor is. So if you do fluid dynamics and stuff and you start working, or elasticity and stuff, the most basic idea of a tensor, and it's not the correct one, but it's just get your intuition going, it's simply a matrix. Okay, so a tensor is basically a multilinear map from vectors or dual vectors. Okay, and I'm going to define dual vectors in a moment. I'm surprised I haven't done it already. It's a bit worrisome. Okay, into numbers, and so, this is just the basic intro example. Okay, so a tensor is a multilinear map from vectors or dual vectors, which is still coming, into numbers. Okay, and just an example is the stress energy tensor on a body. So suppose you have a box, right? And you want to see how the box responds if you push it, right? So depending on the material, if you have like a Tupperware, like this, a very stiff Tupperware, if you push it this way, it like resists you. There's a certain maximum amount of normal force that will actually, before you crush the thing. If you push it this way, you have a shear force. In other words, you want to make it look like an egg carton or like the beer boxes that you collapse. You want to look there. You sort of apply the force in a different direction. You also want to keep track of how the thing deforms. And it need not be the same. Like some materials is easy to squash, but very easy to push to the side. Okay, so that's in some sense the shear force. So if you want to keep track of the response of the body at each point to forces in different directions, then one, you actually need an indication of where you're keeping track of, okay? And then you need an indication of the different directions, Okay, so then you basically get a 2-index quantity that says, suppose you look at this face, and these things can differ. You can like make this thing like several layers of cake, so it's going to move easily in that direction, but it's going to move harder in this direction. And then if you think about it, then this surface and this face will have completely different properties. Okay, this face will move easily in that direction, but not easily in the vertical direction. So the way you keep track of those things when we do elasticity, and this is actually where I encountered tensors for the first time, was I went to work at the Atomic Energy Corporation, and there they were doing diffraction of X-rays and seeing how X-rays bounced off various materials, and they wanted to be able to reconstruct features of the materials from it. And so in particular, they wanted to measure whether how the material was elastic or not simply by looking at the atoms. And so they had a black box machine that was trying to tell them that. And for some reason, this material that they were looking at was not fitting into the way the black box worked. And the guys had quite a big contract and they were desperate. And the guy said, well, they use tensors and I don't know how to use tensors to make the black box, but here's a book. And then so I spent 3 weeks teaching myself tensors before it was ever taught here. But so this elastic example of this idea that you have a surface pointing in a particular direction for your material, and then for that surface, you also want to look at the response of forces in different directions, basically results in a 2-index quantity, one labeling which surface you're looking at, and then the second number labeling what the forces do in the various directions. So a way of thinking of this tensor is simply a way of storing information about 2 different vectors. Okay, and in fact, the stress energy the stress tensor we use it a lot in elasticity. We use it a lot in in fluid dynamics. You look at the stress tensor within the fluid. So some fluids shear very easily in one direction and not in others. And in fact, the blood is a fluid with a very weird stress tensor because it's made out of the red blood cells.
Yeah, I remember last year Dr. created when dealing with the stress tensor.
Yeah, so
Or something like the blood
it's not known. The only thing we know about the blood is that it has it has a stress tensor, but we don't know what it is. But yeah, you use it a lot in fluids.
So you check the stress tensors for inside and outside for implosion and explosion?
So all the stress tensor does is okay. So the stress tensor keeps track of the forces on the material. And then depending on what the material is, it responds differently to different forces. So it doesn't actually tell you, it's just, for this example, it's just the container in which you store your information. It's like if I have a force that points this way to this face, this is going to be my response. Okay, and yeah, it will ultimately, if you know what the tensor is, then you can describe the whole material by that way, and you can work out whether it's going to have elastic deformation or plastic deformation, whether it like shears or whether it actually breaks. Okay, so all the tensor does is it's the container, like the matrix, that stores the information in a way that's structured while taking into account that you have one vector and a second vector. It's basically a box that keeps information for things that change in 2 different ways, for 2 different directions. But I just wanted to give you, in some sense, a feel for where you use it, and then how, sort of, at least a practical feel before I start introducing the formal definition for what it was. Okay, so before I do that, in this definition, there's this thing called a dual vector space. And I wanted to define that because that is, remember right in the start, I said, if I write an index up, don't dare change it without a reason. Okay, and this is the reason. We've defined vectors as very closely related to derivatives, right? Derivatives in a particular direction. Okay, now a dual vector space is not a vector space, but it is very closely related to your vector space. So what a dual vector space is basically if you have a vector space, okay, over real numbers. So this is just an ordinary vector space. And for example, a tangent space that we have in all our manifolds so far, then there's a collection that we call V star. Okay, and these are linear maps that are maps from the vector space to R. Okay, so remember your vector space was something that operated on functions from your manifold to R. Okay, the dual space operates on vectors, maps vectors to R. Okay, and it has addition, scalar multiplication defined just in the normal vector space. Okay, so the object that the dual vector space is mapping to R is different from the vector space. Okay, there's a difference. So all you have to remember now, there's a definition for my vector space that operates on functions on the manifold, mapping them to R. And then there's a dual vector space that actually works on the vector space itself and maps that to R. And so, and it also has the properties of a vector space or a vector space structure, but it is not the vector space. Okay, so this thing has addition, scalar multiplication in all the normal ways, and it basically behaves like a vector space, and we call this V star to be the dual vector space to V. Okay.
So just tensors is not vectors or dual vectors, it's actually just dual vectors.
No, it's both.
Okay, so
Okay.
or is for both.
In a tensor, it's a multilinear map, so it's linear in many inputs. Okay, and some of the inputs are vectors, and some of the inputs are dual vectors. Okay, and they behave differently. So this is the main thing you have to take. The vectors are different from the dual vectors. The vectors, the components, we usually have up indexes, and the dual vectors, we usually have down indexes. Okay, and I'm going to tell you exactly what the dual vectors are at the moment, in a moment. The elements of V star are the dual vectors. So all at this point in time is you have two things that have vector space properties. One is your vectors that are associated with directional derivatives. The other one are your dual vectors, and they map vectors to R. Okay, and your dual vector basis, this is where it comes in. You can write, because this thing is a vector space, your dual vector basis you can make up in the following way. You basically make up the basis of your dual vector space from the basis of your vector space. Okay, in the following way, you simply define them as elements, okay, that have the property that if you use that element and you apply it to your vector space, then you get the delta function. Okay, so you are defining your dual vector basis from its action on the vector basis that you already have. Okay, so for example, what you do is you look at all the basis vectors for your vector space that you have, and then you define, you say you have elements in your dual basis, and their property is that if you take, say, the first element in your dual basis and you apply it to the first element in your vector basis, then you're going to get 1. Okay? And if you take the second basis in your dual basis and you apply it to the first element in your vector basis, you're going to get 0. Okay? So in some way, it's like an inverse basis. But this is the rigorous definition. You have your vector basis that you're given from your manifold. Then you have a dual basis that we usually indicate with stars. And that's the basis of your dual space. and they are entirely defined by the fact that their action on the vector basis gives you this, is 1 if they have the same number and 0 all the other times. Okay. So this delta VU is 1 if U is equal to V and 0 otherwise. Okay. So you basically define the action of the basis elements of your dual base on the basis elements of your vector space, sort of with basically this thing, the basis vectors, and the fact that they are basically linearity. They basically, it is a vector space, so the action is linear. Okay, and so any other vector in V star behavior, if you express it on the terms of this basis, you actually know what the behavior is. Okay, so suppose you now have an arbitrary vector in V, okay, your original vector space. You can basically say your, and you have an arbitrary vector V star that is basically some coefficient times this basis. You can simply work out what it is because you know that these V stars, whenever you hit the basis of the dual vector space, you're going to have this delta V mu coming in. Okay, and therefore what you have is that this thing is the basis for V star. Okay, and you also have, because there's a one-to-one relationship between these two, that the dimension of V star is the same as the dimension of V. Okay, and so in some sense, because the basis vectors are connected but not the same, very often when we work in Rn, these two things look as though they're the same, but they're not. Okay, because they are connected but not the same, there's a way of an isomorphism between V and V star. Okay, but it depends on your choice of basis. Okay, so and so because it depends on your choice of basis, there's no natural way of generally identifying V star with V if you don't have the particular basis. Okay, so let's just stop there, and I actually want to maybe make an example. And huh?
The engineer.
Yes, please. Okay, so I'm going to make an example of